This is section 10.3, thus the cross product of two vectors. These are the objectives. Find cross products of vectors in space, use geometric properties of cross products of vectors in space, and use triple scalar products to find volumes of parallel pipettes. Let's move on to the next slide. The cross product of u and v. So here's vector u, here's vector v. The cross product is given by the following. This is how we represent cross product by this x. Cross product of u and v is equal to the determinant of this matrix. When you find the determinant of this matrix, it's very important to know that you actually get another vector. Let's move on to the following. And if you take any two vectors and you take the cross product, you're going to notice that all of these are satisfied. Let's move on to the next slide. The properties of cross products are valid where theta is the angle between u and v. So these are like formulas. First formula, whenever you find the cross product of two vectors, that answer, which is, like I said earlier, is a vector, is going to be orthogonal to u and orthogonal to v. And you'll see this better in an exercise that we're going to be doing in just a little bit. B, you have the cross product. If you take the magnitude, it should equal to whatever this is, the magnitude of u, the magnitude of v, times sine of theta. So this is another way you can find an angle between two vectors. C, the cross product of u and v is equal to 0 if u and v are scalar multiples. And D, we're going to be using this one. The cross product plus the magnitude gives you the area of the parallelogram, having u and v as adjacent sides in the parallelogram. You have more. This has to do with volume, the absolute value. So you take the determinant and you take the absolute value of the triple scalar product is the volume of the parallel piped having vectors u, v, and w as sides. And I will illustrate this a little bit better with an example that is coming up soon. Let's move on to the next slide. And and keep in mind, this is actually this is generating a determinant, which is an actual number, scalar. Let's move on to the next slide. Here's number 1. It says find a unit vector orthogonal to both u and v, so to vector u and vector v. Here's the formula that we're going to be using. It looks familiar to something you have seen in the past, which is basically all you need to do is you need to find the cross product of the two vectors and then find the magnitude of that cross product. So here we go. So this is how you find the cross product of the two vectors. You find the determinant. Remember, this is how we did it earlier. This is how you compute the determinant. Then you take this times, this times this times this, and you write it here, minus the product of this times this times this, and you simplify, and this is what you get. This is a concept that you have seen in the previous section, so for the most part is review, but you should be able to follow how we get this. And once you simplify, you get this vector in component form 271. So this is the numerator. So now we need to find the denominator, which is basically the magnitude of this vector. Once you do that, you end up with 3 radical 6, and which means that the unit vector orthogonal to both u and v is the following: 1 over 3 radical 6, and then, this vector. You can rewrite it the following way if you like. 271 over that. Yeah, same thing. Let's move on to number 2. Now we need to find the cross product again, and we need to show that it is orthogonal to both u and v. So let's find the cross product of u and v. You find the determinant of this. Once you do that, again, you multiply this times this. You're going to get some answer. You put it here, and then you find the you multiply this, and whatever you get here, you subtract that from the first product. Then this is what you get. And again, if you want me to clarify this in class, I'm more than happy to. Just let me know. But this is something that you, like I said on the previous slide, that you did on an earlier section. Then at this point, this is my, I'm going to call this vector W. So I'm going to show that vector W is orthogonal to U, and orthogonal to U, and orthogonal to V. So I take the dot product now of U and V, and I end up with 0. And remember, if it is equal to 0, it means that the two vectors are orthogonal. And you also do V times W. V times W. You take the dot product, and you can notice that it is equal to 0. And it's very important that you understand there's a big difference between, W is, so this is how you answer the question. W is orthogonal to both U and V because we just showed that. And like I was saying a second ago, it's very important that you clarify, that you're clear on what this represents and what this represents. Okay? This is the cross product, and notice that you get a vector. This is the dot product, and notice that you get a constant, a scalar. Let's move on to the next slide. Just find the area of the triangle with the given vertices. Here we need to compute the area of the triangle. So we're going to use a formula you saw earlier on this video. So basically this is how you find the area of the parallelogram, but since I have a triangle, I just multiply it by half and I'm done. So then all I need to do is I need to find the component form of vector AV, AC, and you know how to do that. Terminal point minus initial, and then you end up with the following two vectors. And then I take the cross product, I find the magnitude, and I multiply by half. That's why you see this. This is the cross product. You find the determinant of this, and then you do this part. You simplify, and this is what you get. Negative 6, 6, 18. Once you have this cross product, you find the magnitude of it, and you multiply by half. Here's the work, and you end up with this as your answer for the area of the triangle. 3 radical 11 square units. Let's move on to number 4. So here's number 4. For this problem, it's going to be good if you actually use dot paper. Here we go. For the following, part A says verify that the points are the vertices of a parallelogram. Part B, find its area. C, determine whether the parallelogram is a rectangle. There are the points A through D. Let's go ahead and graph those points. So here's point A, here's point B, here's point C, and here's point D. So now I'm going to actually I'm going to sketch the parallelogram that these 4 points generate, which is there. Then I'm actually going to find part A says verify the points are the vertices of our parallelogram. So I compute AB and CD, and I notice that I have the same vectors, which means that they are parallel. Then I'm going to actually compute the distance of or the magnitude of AB and the magnitude of CD, and I end up with radical 14, which means that they are opposite sides of this quadrilateral have the same length. Since I have opposite sides that are parallel and the same length, in geometry you learned that that's enough for you to conclude that this represents a parallelogram. Part B, find the area. So this is what I'm going to use. It's basically the magnitude of the cross product of U and V. So this is going to be my U and this is going to be my B. So I find AC, which is 5 for 1. This is the component form. So I take the cross product of AB and AC, which is what I have here, excuse me, and then I end up with this. And then I take the magnitude of this vector, and that should give me the area of this parallelogram, which gives me 2 radical 83 square units. And then the last part, this says determine whether the parallelogram is a rectangle. The way that I'm going to do this, I'm basically going to take the dot product of AB and AC, and I end up with something that is not 0, which implies that this is not a rectangle. It would be a rectangle if this would equal to 0, because this would be 90 degrees. Let's move on to number 5. It says use the triple scalar product to find the volume of the parallel pipe having adjacent edges U, V, and W. So here's where I have to use the determinant. This is the formula you saw on an earlier slide. And I just need to find the determinant of the matrix generated by these 3 vectors. And it's going to be easier if we look at these 3 vectors in component form, because the matrix generated by the 3 vectors is the following, which is basically 113, 033, 303, which is what I have here. Then I go ahead and find the determinant of that, and I end up with 9 cubic units. This is the answer to number 5. It's actually pretty easy. Let's move on to number 6. It says use the triple scalar product to find the volume of a parallel pipe having adjacent edges U, V, and W. And I want to go ahead and actually graph the 3 vectors that you see here, U, V, and W. And this is the vectors that you get. And I also added the following. So this is the component form of these 3 vectors. But look at the following. This is actually the parallel pipe that is generated by the 3 vectors. So we're going to compute the volume of this 3-dimensional figure. I use this component form to generate the matrix, which is this, and I find the determinant of that matrix, and I end up with 12 cubic units. And this is the answer to number 6. Let's move on to the last one, number 7. This is going to take a little bit of work, but nothing we can handle. It says find the volume of the parallel pipe with the given vertices. So if you were to plot all those points, this is what you get. This is the parallel pipe that you get, this 3-dimensional figure. So what I'm going to do to find the volume, I'm going to actually find vector AD, AB, and AC. And I know how to do that as long as I use a terminal point minus initial point. And here's my 3 vectors. And then once I have this information, I need to find the determinant of the matrix generated by these values here. 110, 021, 102, and 011. Once you find the determinant of this matrix, you end up with 3 cubic units. And this concludes the video.